isomorphic to A prime tensor in E prime. Not the set of equivalence classes of Algebraic algebra forms a group under tensor product operation. It is called usually it is called the Algebraic group of Y. And, there is another definition of Brouwer group. It is called cohomological Brouwer group of Y. It is defined to be the torsion part of the second homology of Y, ethyl homology of Y, GM coefficient. Now, when Y is smooth, it is known that the second cohomology group is actually torsion. It is due to some result of growth index, and thus the cohomological Brouwer group is actually the whole H2 when Y is smooth. And giving an Algebraic algebra over Y is equivalent to giving a Brouwer-Savary scheme, that is a projective bundle on Y in the ethyl topology, because all the, Algebraic algebras and the projective bundle in ethyl topology, they are parameterized by this set H1 Y is PGLN, because the automorphisms are PGLN of projective bundle and Algebraic. And the Brouwer class of a projective bundle can be thought of as the obstruction for P to being projectivization of a vector bundle. And if the Brouwer class vanishes, then you can conclude that the projective bundle is actually Zariski locality. It is taken to be ethyl locality, but Zariski triviality is stronger than it. The sequence of cohomologies associated to the exact sequence it gives a homomorphism. If you look at the long exact sequence of cohomologies, you will get a homomorphism like this: H1 Y PGLR to a cohomological Brouwer group of Y. And if you vary this R, this mu R SLR, if you vary the R, you will finally actually get an injective group homomorphism from the Algebraic algebra to the cohomological Brouwer group. Sorry, Algebraic Brouwer group to cohomological Brouwer group. And by a theorem of Gabor, it's known that actually it is highly scientific. The result of Gabor is actually unpublished. And De Jong gave a different proof later. Since it's cohomological, so as we can see, for smooth varieties, we can take the definition of Brouwer group to be the second cell cohomology of Y with GM coefficient, and this can be generalized to stack. For algebraic stack, the Brouwer group of Y with mean its cohomological Brouwer. The Brouwer group useful in studying rationality questions. If two we have two varieties, y and y prime, which are smooth and birational, then it can be proved that their Brouwer groups are isomorphic. And like, for example, it is also known that when K is algebraically closed, the Brouwer group of K is 0. So the necessary condition for a variety to be rational is that its Brouwer group should vanish. I mean, and you have to prove that the Brouwer group of the projective space is same as the Brouwer group of the underlying field over which the projective space is defined. But assuming that vanishing of Brouwer group is necessary for a smooth variety to be rational. So, to know whether a variety is rational or not, we can try to compute its Brouwer group. I mean, to get some idea. And, I should also just mention that most of you know that H1 of YU is a GM coefficient, the parameterized line bundles on Y. Similarly, Brouwer group H2 of GM also parameterizes something called GM Jarvis on Y. Has some geometrical the elements of H2 has some geometric interpretation. And now I'll define some basics on parabolic bundles. Let X be an irreducible smooth projective curve of genus data equal to 2 over an algebraically closed field of characteristic 0. Let E be an algebraic vector bundle of rank R over X. Fix a subset of S distinct closed points on X. The parabolic data of rank R for points of S consists of the following collection. So for each of these marked points, I assign a set of positive integers mi1, mi2, mi such that they add up to R, and an increasing sequence of real numbers alpha 1i, alpha 2i to alpha I between 0 and 1. Parabolic structure on E over S with parabolic data as above consists of the following. So for each of these marked points, we are given a weighted filtration of the fiber of E over Pi, and we are given a weighted filtration like this. Weighted filtration just means a filtration with such alpha is attached, and such that the MIJs are exactly the dimension of the successive quotient. The above collection alpha, and let me call the full collection alpha ij by alpha. It is called the set of weights, and the integers mij are called multiplicity of the weight alpha ij. By a parabolic bundle, we mean a collection of these data, where E is a vector bundle on X, and M and alpha are described above as above. So alpha is the collection of alpha ij's, and M just encodes all the MIJs as similar to alpha. will denote a parabolic bundle in a short form by this T star. Let T star be a parabolic bundle of rank R. The points are not part of it. The points are fixed ones and for this. The parabolic degree of T star is defined as the degree plus the summation Mij alpha ij, varying over all the parabolic points and all the indices, and the parabolic slope of each star is defined as the parabolic degree of star by star. A parabolic bundle called parabolic semi-stable for every proper subbundle F in E. We have the parabolic slope less equal parabolic slope of F star is less equal to parabolic slope of E star. I mean, given a subbundle of E, there is a natural way to induce parabolic structure on F by intersecting the fibers of F with the filtration of E and assigning the weight in a proper manner. Then, so by F star, I mean F with that induced parabolic structure. The parabolic morphism between two parabolic bundles is a morphism of the underlying bundle such that for each parabolic point P, and if alpha I P is greater than alpha J prime P, then the fiber at the fiber phi should take the I mean, it should be filtration. It should be either compatible with the filtration in some suitable sense. System of weights is called generic. Every parabolic semi-stable bundle with weights alpha is parabolic stable. Let this PM alpha X R right denote this as the coarse moduli space of its equivalence classes of parabolic semi-stable bundles over X of fixed rank R and determinant psi and its parabolic data M alpha. And this moduli was constructed by Mehta and Seshadri. It's a normal projective variety whose smooth locus consists of the classes of parabolic stable bundles. And when alpha is chosen to be generic, as the definition above, then the moduli space is actually smooth, because in that case, any parabolic semi-stable bundle is parabolic stable. So it is smooth one. So we'll be mostly working with generic weights. So you can you can assume for most of the time that the moduli of parabolic bundles is smooth. Now,
generic way to the filtration for each point. Filtration of so if the order technique, given the filtration of the generic way.
generic code may not always exist. So there is some condition on the GCD of the greatest common divisor of the rank, degree, and the MIJ. So if the total if the GCD is 1, then it always exists. That's some result proved by Yokogawa and Poland. It may not always exist. Come to moduli of GLR bundle. Let gamma be the group of R torsion points in the Picard group of it. It can be shown that it is a finite group of order R power 2. This group gamma acts on the moduli space of the stable vector bundles of rank R and determinant xi by tensoring. Let I be positive integer between 0 and d minus 1. D is the degree of that. Sorry, I missed an I there. Should be I congruent to D mod R. The force moduli of stable PGLR bundles over X will denote it by NRI. It's defined to be the quotient of in R psi by the subgroup gamma. Okay. This fixing I is like fixing topological type. PGLR has pi 1 Z mod R. The I is like fixing the
Finding the amount. Are you saying that this quotient is really the amount? Find it like that, why?
by moduli by coarse moduli. I mean that it has the properties of coarse moduli space.
So you can't define define this to be more.
Okay. It is not like yes, there is not a unique choice.
Until you define something, define normalize the space. So why should this quotient have that?
Okay. You can check that it has the properties like coarse moduli should satisfy the universal property. Immediately, the moduli stack of stable PGLR bundles is taken to be the quotient of script n means the moduli stack of stable vector bundles determinant isomorphic to xi. Yeah, you can take the quotient or you can also think of it as no, you can think of it as the quotient stack. In RZ mod gamma, you take the quotient stack. Clip that yes, yes. Mod yes, but when if the action is not free, you can take the quotient stack.
First line, that question is in the category of
Yes, yes. Yeah, I'm not claiming it is smooth or anything.
I am asking why.
Oh, this is some general. There's a that any quasi-positive variety to take some finite group action always exists. The quotient always exists.
Like that.
Yes. Because something like any finite set of points, you can find the gamma equivariant affine open. You can contain inside some gamma equivariant affine open, and you can glue the affine opens to get model. I mean, this is the general fact that under finite group action, only quasi-positive variety quotient always exists as a scheme. There is a natural morphism from the moduli stack to moduli space, the post moduli map. And go to some known results about power groups of these moduli. So Balaji, Viswas, Gabbard, and Nagaraj proved that the sorry for the mix-up notation. So this M Arza is the same as this N Arza. M X Arza is the moduli of stable vector bundles on X of rank R and determinant I. I think the Brouwer group of this moduli is known to be Z mod as the GCD of R and was proved by Balaji, Biswas, Gabbard, and Nagaraj. So the generator is obtained by restricting the universal projective bundle on X cross MRZ to some point cross MRZ. And they proved that this actually generates the Brouwer group. Later, Biswas and they generalized it to the case of parabolic bundle, the moduli of parabolic bundle. To prove that the Brouwer group is isomorphic to Z mod N, and N is the GCD of E, R, and all the multiplicity. Biswas and Fogati proved.
Can you say what's the difference of?
The approach they took was they did it for small weights first. So there is a forgetful map from some open subset of this parabolic moduli to the moduli of stable vector bundles, and they considered the pullback of this projective universal projective bundle on X cross M under that forgetful map and restricted it to some point and showed that it actually generates. And after doing it for small weight, they did it for arbitrary weights by studying how the Brouwer group changes. I mean, how the moduli are related under wall crossing. So that is how they proved for all weights, all generic. This was in Hogari proved that the Broward group but this should be the smooth locus of NRI. The Broward groups of the moduli stack of NRI and the smooth locus of the post moduli NRI coincide. Remember, this is the moduli of stable PPLR bundle, and it fits in the exact sequence like this. These are some known results. Similarly, you can look at the action of gamma on the parabolic moduli as well. This acts by tensoring, and that tensor L will have the obvious parabolic structure coming from stat, and this as we defined earlier, we can define the moduli and the force moduli of stable parabolic PLR bundle denoted by P and M alpha Ri is defined to be the quotient of it's taken to be the quotient of the parabolic moduli by the subgroup gamma. Okay, the same problem. And similarly, you define the moduli stack for parabolic PGLR bundle. And this stack is a Deligne-Mumford stack because points have finite stabilizers. Prove that when in the case of full flat, the Broward groups of the moduli stack and the smooth locus of moduli force moduli coincide, and when GCD and in the first case we are working with full flags. The second case we allow partial flags as well, but under the condition that the GCD of them should be 1. GCD of rank, degree, and multiplicity should be 1. Let this Pn alpha Ri cap slip smooth. Sm will denote the smooth locus of the moduli. Then we have Broward group to be isomorphic. Its Broward group is isomorphic to H2 gamma K star mod B. As you remember, we saw H2 gamma K star mod H getting here again. Can be described as Broward group of the parabolic moduli of the moduli of parabolic scalars. Little more than half an hour. Half an hour. Keeping rank, degree, and determinate fixed, let us denote Pm alpha to be the force moduli of parabolic PGLR bundle, and Pn alpha to be the Pm alpha to be the force moduli of parabolic bundles, and Pn alpha to be the force moduli of parabolic PGLR bundles. now I'll get into the proofs of this theorem. So as we saw earlier that gamma acts on the parabolic moduli, and for some non-trivial point in the non-trivial absorption point, the Jacobian, let Pm alpha L denote the locus of fixed points on for the action of L on Pm alpha. Let M be the order of L. So yeah, let M be the order of L. So in particular, M divides R. Since L power R is trivial, we can choose a non-zero section of L power M. So since M is the order of L, we can choose a non-zero section of L power M from S naught. And we can define the spectral curve for this section to be set of all points in L such that V tensor we have to M times it is in the image of S naught. So more precisely, it is the pullback of the closed embedding S naught under the morphism L to L power n given by V goes to power and V tensor we have to M times. And the gamma denotes the restriction of this projection map. Gamma denotes the restriction of the projection from L to S to YL, because YL is a subset of L. You can restrict the projection to YL. One can check that gamma is an Galois morphism of two curves with the Galois group as mu F. And the action of Galois group on YL actually arises from the C star action of L. C star action on L. So isomorphism class of this covering does not depend on the choice of section S naught. When subshot is given any order M line bundle, you can find an entire Galois morphism on X of TVM. Now, there is a well-defined notion of direct image and pullback of parabolic bundle for such entire Galois morphism. It was done by Iswas and Gabriel for more general case. They also consider ramified covering, but in our case, we just need the entire Galois case. Galois morphism case. So S is the set of parabolic points fixed for X. Then when you give parabolic structure for bundles on YL, the set of parabolic points should be taken to be gamma inverse S. Now, getting to the proof of theorem 1. For convenience, assume that we have a single point, and these are the set of parabolic weights at that point. So, given such a set of R distinct elements, that P alpha denotes the set of all possible partitions of its elements into M subsets. each containing R by M element. So remember, M is the order of the line bundle L we are working with. For each such partition, let MT YLND denote the moduli space of stable parabolic bundle on YL of rank N degree D and having full flat parabolic structure at the points of S according to the partition T. It's some
Sorry, can you remind why M twice R?
Because we are taking to be the R torsion points. M is the order of L. Is it okay?
No, I don't understand. I'm asking why.
So we're assuming so we're taking R torsion line bundle.
Let's say what that means about L for M is trivial. We think L for M is trivial and L for R is trivial. And M is the order.
Yeah, the order of the group is R power 2. That is different. So there is the way to describe parabolic weight, parabolic structure upstairs using the partition. I won't get into the full detail. Let script in T. Let it denote the subvariety consisting of stable parabolic bundles F star such that the determinant of the push forward is isomorphic to right. And you take the disjoint union of this moduli for each T. The lemma is when we are working with full flat. We're working with full flat, right? And then there is a surjective morphism from this NL to the fixed points.
What is full flag? What does full flag mean?
Sorry, full flag. I didn't
Rank one.
Yes, full flag means each successive quotient has rank 1. The multiplicity is 1. Then there is a surjective morphism from NL to the fixed point PM alpha L. And the fixed points under L given by the parabolic directive under the eternal gamma. I just wrote the lemma here again for convenience. Just give an idea how to prove it. So it is saying that any fixed point can be obtained as a push forward of some parabolic bundle. That is what it is saying. So if you start with some parabolic bundle on YL, I mean some element of NL, and consider its parabolic push forward, then it is not difficult to show that it is actually a fixed point because there exists a tautological trivialization of the pullback of L on YL. So there exists a tautological trivialization of gamma upper star L, which induces an isomorphism. And that induces an isomorphism for F2 from F to F tensor gamma upper star L. And then you can just take the push forward and use projection formula to get that E, the push forward, if E denotes the push forward of F, then E is isomorphic to E tensor F. And you can check that everything like preserves the parabolic structure. So the image of F lands inside the fixed point. The main point is to show that it's surjective. I'm just saying that the image lands in the fixed point. Now to show F is surjective, we start with some E star below, which is the fixed point. So there is a parabolic isomorphism given. And suppose the weights are given by this alpha 1, alpha 2, alpha r. Then after suitably modifying phi, we consider its pullback and compose with the tautological trivialization again to get a morphism from gamma apostoli to gamma apostoli. So one can show that under new map phi, gamma apostoli breaks up into its generalized eigenspace subbundle, and moreover these subbundles are permuted under the action of the Galois group on gamma apostoli. Right. The pullback of a bundle is a Galois gamma equivariant bundle, and the action will permute the generalized eigenspace. And if F is the subbundle corresponding to eigenvalue 1, one can show that its push forward is actually. And next, we have to induce a parabolic structure on F with the gamma inverse S as fixed point, so that everything happens in the parabolic setup. And for this, the key ingredient is the following lemma from linear algebra. If you have a diagonalizable automorphism of k vector spaces of dimension r with some filtration, such that the map preserves each term in the filtration, then you can find basis of eigenvectors for psi, such that each Vj can be written as can be built up from this eigenvector. Use this, you can show that you can because the main point is in the first line, so if T is the push forward of F, then the fiber of P is actually direct sum of SQy. So somehow you have to use that with this linear algebra statement to get the parabolic structure above, and you can show that the push forward is happening in a parabolic manner. That proves the lemma. And you can show that F star is also parabolic stable. And in computing dimension, we have this following result that the codimension of the closed subscheme. And if you take the union of all these fixed point locus for all the non-trivial elements in gamma, codimension of the closed subscheme is at least 3. And then you look at the complement, which is gamma invariant. And on this, the action of gamma is now 3. You look at the quotient, lands inside the smooth locus of parabolic, in the smooth locus of moduli of parabolic PJR bundle. and it's an open subset of whose complement is of codimension at least 2. And next, to show that in any parabolic VGLR bundle lying in this set has trivial automorphism group. Because if F star is a non-trivial automorphism, then it actually induces an automorphism of the underlying positive bundle. It comes from a map from E to E tensor L naught for some line bundle L naught. And taking determinant follows that L naught is in gamma. But yeah, and also it respects the parabolic structures. So we get an isomorphism of parabolic bundles so that L naught is in gamma, but by our assumption, I mean the way we construct with two is that the action of gamma is actually free, so that will force that L naught must be trivial. So it's an automorphism of E star, but E star is also parabolic stable. So it is multiplication by some non-zero scalar multiple. But then on the projective bundle, the map must be. So it shows that on U alpha mod gamma, the points have trivial automorphism group. Then the force modular map restricts to an isomorphism over the subset, the open subset U alpha mod gamma. And finally, there is some purity statement for Brouwer group. Says that for a smooth scheme and a closed subscheme of codimension at least 2, the Brouwer group remains isomorphic if you remove the closed subscheme. You also check that this still holds true while the telling of first step. Then you can finally get the statement of theorem 1. Complete the proof for theorem 1. Now I'll get some ideas for proof of theorem 2. I'll restate the theorem here again. So now we work with partial flags as well. So let GCD of degree, rank, and Mij to be 1. This condition is basically there just to ensure that generic will actually exist. Not a big. So then you can show that the Brouwer group has this description. And also holds for some particular type of non-generic weights as well. Yeah, so first we do it for sufficiently small reds so that there exists a morphism from EM alpha to the semi-stable, the modular of semi-stable vector bundles of fixed determinant light, which forgets the parabolic structure. You skip pi over the stable locus, that is the modular of stable bundle, and it is a surjective map whose each fiber is a product of flag varieties. And can be shown that it is actually an HR local trivial fibration. And as we saw earlier, that similar statement actually holds for the model for the usual moduli of vector bundles and the closed subset, which is the union of the fixed point locus for different gamma, so for different non-trivial elements in gamma has codimension at least 3. So consider the complement, then you can check that the action of gamma. First of all, the map pi is clearly gamma equivariant map, and if you restrict the map over Q, then the action is seen to be free, and the four-dimension estimates again show that they keep the Brouwer group of local. Then you consider the finite ethyl cover, the two finite ethyl cover. Then there's for finite ethyl cover, there is the Cauchy state spectral sequence, which will actually produce the following two exact sequences. I'm skipping some details. So you have the two exact sequence like this, and where the H is actually the subgroup cokernel pi upper star. That is how this and Hogadi gave the description of it. So we take H prime to be the cokernel of pi prime upper star. And then we relate these two exact sequences and actually show that this under the map pi induces an isomorphism from H to gamma k upper star to H to gamma k upper star, which takes to H prime. Then from that sequence 6, you can show that the Brouwer group of smooth locus of parabolic PGLR bundles actually is. And so this is done for small weights and for arbitrary generic weights. Just use that given quasi-parabolic data means just the collection of multiplicity. We are not fixing the weight. Okay. So given a quasi-parabolic data, the set of all possible weights for this data forms this simplex. It has some finitely hyperplane section called wall, which arise from parabolic semi-stability condition. The generic weights are exactly those which lie outside this wall. I mentioned it a couple of times that under the hypothesis on the GCD, we know that such a generic weight always exists. The gamma be a weight which is not generic but lies on a single wall, so that it does not lie on the intersection of two or more walls. Then in a small neighborhood of gamma, we can find two generic weights, alpha and beta, which are separated by single wall W only. And gamma is the intersection of line joining alpha and beta with W. Then it can be shown that any alpha parabolic stable bundle is actually gamma parabolic semi-stable, which induces a gamma equivariant morphism from M alpha to M gamma by simply replacing the weight. Note that M gamma is no longer two similar kit as we did before. Consider the open subset of gamma parabolic stable bundle. You can, and by a result of Borden group, known that the map phi alpha that we define here by replacing the weights is actually an isomorphism over Q gamma, and both of these open subsets have complements of 4-dimension matrix group. And then you basically remove the fixed point sets from these two open subsets, so that they are still gamma equivalent isomorphic. So by simulate it. I'm not going into that. So finally, by doing a simulate it as before, you can show that the Broward group of the smooth locus for T and alpha is same isomorphic to the Broward group of locus of T and gamma. You can replace alpha by beta to get isomorphism. And finally, we already did it for small waves, so we can do this word crossing type of argument and start with a single, a small generic wave and cross one wall at a time, conclude the result for all generic. These are some references for the
Questions?
which are so for example, for parabolic modular parabolic bundle for generic width is known to be rational. That is done by Golden Yokoga.
And you are only proving the smooth
Yes,
and then say that
yes, we are working for the on the smooth local because we want to use the purity statement. That for that we want to restrict us to the smooth part. But the other
varieties are rational
that I don't
The broad for big open and the
so that statement is take for positive variety.
I think the Browser group, sorry, the group that we got a description like H2 gamma tester model. I think that is not trivial.
No, so that there is not enough, but my question is whether that modular variety is bigger height, not whether it is that.
I don't know. I mean, then the smaller ones should also be. I mean, the open subset should also be that. I mean, to be in order to be rational, the Browser group should vanish. But
Anything else?
so the Browser group is not vanished.
Anything else? Okay, so let's thank Studio again. We are running behind time, so maybe let's have only a 5-minute break. and she talk about droplet deformations and F singularities.
Thank you for giving me the opportunity to talk here. So I'll talk about problem deformations and its similarities. This is my joint work with Matthew Barbaro.
She'll write on board.
Right.
The voice is very
Now, so here are we always the commutative Nigerian ring. With identity of prime characteristics. And then the advantage of prime characteristic is we have provenience. Like which sends an element to its pth power of provenience. Yeah. So in prime matrix it is a ring endomorphism. And provenience plays an important role to study singularities. For instance, a ring R is reduced, that is, it does not have non-zero nilpotence. So if and only if the provenience is injective map. The second, we see what provenience does on polynomial rings. So suppose my ring R is just polynomial invariable, then R is pre-model over f of R, the image ring and provenience, which is same as this with basis so on polynomial rings, provenience gives the pre-model structure. Now more generally, it's a classical result by Kunz. A ring R is regular if and only if the provenience is a flat map. And once it is flat, it can be checked at once that it's a faithfully flat map. So once if that is faithfully flat. And then we want to relax this condition, the flatness condition or the freeness condition in various ways. And then using the relaxing this condition, several kinds of singularity has been introduced. Altogether, they are called F singularities. So relaxing, make it more clear what I mean by relaxing the faithfully flat text or the freeness of Frobenius, various kinds of singularities have been defined, and altogether we are called its singularity. So here X stands for Frobenius. Okay, so I'll talk about only four fundamental type of singularities. So first one is F regular. Second one is F rational. Third one is F pure. Fourth one is F injective. So a pure singularity meaning that the Frobenius map on R to R is a pure morphism. So faithfully flat implies pure, so hence it's a generalization of this. And again here, so pure meaning that on the finite case it just gives splitting. And so if injective meaning we do not need to be for arbitrary modules to be injective, we just need the local homology module.
So Frobenius map and what does
Sorry.
pure what does
In general, pure means if I consider any R module and if I tensor, then it remains injective. But I'm saying when the Frobenius is, it is for any finitely presented module, purity is same as splitting. So Frobenius gives a splitting. So pure means that for any M in R module, R tensor M to R tensor M is injective. The Frobenius tensor identity. Oh, it's not.
it's okay.
Just after the government, not on.
It's okay.
So then I'm saying here we no need to take any arbitrary module, just take the local homology module. The game is any maximal idea. This is injective. And one can see that this map, if tensor identity is just the Frobenius map on the local homology model. So this is the definition of this, but I will not define what is a regular singularity because it gives some technicalities on tight closure. But I will say if regular singularity is closely related to regular rings, that's why this name Frobenius, F for Frobenius and regular, this is closely related to regular rings. And the second one is a rational singularity. I will not define this also, but I'll only say that this ring in characteristic P is closely related to rational singularity in characteristic 0 by reduction mod P. So this is reduction mod P, rational singularity. In characteristic 0. That's why it's named. And there are relations between them. Like if regular implies a rational, again this implies a pure, and if rational implies an injective, and if pure, also injective. This is the relations between. So here, the Frobenius gives a splitting. I mean, for the regular ring, it's a free, right? It's a splitting. Maybe we just need just splitting. Yeah.
Have to go for the whole sector.
It's
also, no?
Yeah.
The map alone. There is a Frobenius.
Huh. No, but that is I think that is a global motion. But I am here only saying the local splitting. Only the
So we can map it, and if you can get a map from R to R.
yeah. So I mean here, if you want to consider this as a module map, then you can write that R to, but we write a lower star R, right? And then I have this. I have a map this way as a where, but here the module structure is given by the provenience. So it's a module map, and then if I go this way, then it will be
That's the view.
yes, that's the splitting. So it will be identity on this. But the map has to be the R linear map. So here it's just a multiplication, but here the module structure comes from the provenience. Right. Okay. So now I will. So this is roughly the definition of the four singularities. So I'll say what are the examples. This one or just I will see some examples. First one is Veronese offerings. Of polynomial rings. Are irregular. So in fact, direct summand of any regular rings will be irregular. And then the second one is that summing, so it's normal, affine semigroup rings. Rings are irregular. So affine semigroup rings, meaning that it's just a K-algebra generated by monomials, and affine semigroup rings appear in combinatorial commutative algebra. It's saying normality is enough to see whether it's a regular or not. The third example is an hypersurface ring. K is the field of characteristic prime greater than 3. Then R is FPO if and only if P is congruent to 1, not 3. But R is not irrational. In any characteristics. So this example shows that F singularities really depends on the characteristics. And these implications are not both ways. It's just a strict implication. So this is roughly about the F singularity part.
Sorry, did you mean, but R is not F regular? Or?
So F rational. Yeah, but in this case, in the Gorenstein case, it will be same as F rationality will be equivalent to F regularity.
Sorry, what was Veronese subject?
Yeah, so polynomial ring. So if I have polynomial ring, then consider this as R. So the Veronese subring will be K algebra generated by all monomials. Sorry, as in all monomials of degree T. Yeah. of total degree d. I mean, the point is that it gives a splitting, and in a direct amount of regular rings are increased. That's all. So now I'll concentrate on the finite, only the rings are finite in genetic K algebra. So my now onwards, my rings are just finite generated K algebra. Psi is an ideal. I love this. So when I is a monomial ideal, I is monomial ideal, meaning that it's generated by monomials, then various properties of, so I maybe, or this is my S, the polynomial ring, then S small I is easier to handle. Various cases. Handle. For example, so S mod R is, in this case, when this is monomial, so sorry, S mod I is reduced if and only if I is generated by square free monomials. So for the monomial ring, monomial ideals, one can see at once and then look at the ideal, one can see whether it's reduced or not. So, but in general, we are not in a monomial case, but given an ideal and a monomial order, one can associate a monomial ideal, which is called the initial ideal. So I'll just write what is initial ideal. So given monomial order, so monomial order, the prototype is the lexicographic ordering, graded lexicographic ordering. Monomial order on S, the polynomial ring, order is the less than on this, and ideal I in S, one can define a monomial ideal it's called the initial ideal of this. So I define what it means. So what is in, I have given a monomial order, and suppose I have taken a polynomial in S. So what is in S? The biggest monomial with coefficient that appear in F. This is my definition of initial term of F, and then initial ideal will be generated by all the elements which are of the form in F. So this is what I can. simple example of in it. So suppose we are again polynomial ring, and then this is the next ordering with x1 x2. The last one is the x. Consider f as the x1 cube plus x2 square plus x3 cube. Then so more generally, given a weight vector the W one can define the initial ideal with respect to this weight vector. I is the ideal generated by the F. So here in the F is now the sum of terms of F with maximum W this. And it is known that given a monomial order n and ideal I, one can find a weight order W such that initial ideal of I with respect to this monomial order can be realized as the initial ideal of with respect to this weight order. And the advantage of writing initial ideal with respect to some weight order is that initial ideal can be realized as a special fiber of a flat family.
Sorry. So the last you need W to be a vector with N or Rn, positive Rn.
No. Zero, I know.
So you need this W to be N or real part of positive real Rn.
No, just integers I need. I mean, one can define the weight order anyway, but I want to state this result that one can find a weight order in then in it. So now the initial ideal and spatial fiber of a flat family. So I am fixing. So So here the notations I am fixing an ideal. And then the wizard. Now what is the variable? T is the variable. Then you find if so, T is the variable, and then I can write this as summation if J. If J is homogeneous with respect to the weight order in W, and then I can define this as summation maybe G. Maybe this one has degree D with respect to again the weight order W. Then write T power D minus degree W in G. Now this becomes a homogeneous polynomial. In A itself but B of this. And we consider the ideal of W I, saying the homogenization of I, the ideal by on its age is I. Now this is an ideal in A. This becomes a homogeneous ideal. Say, but homogeneous with respect to the ordering now W1, Wn, and then 1. So T is given order 1. With respect to that, it becomes homogeneous ideal. And now you consider the ring P. And this ring is called Rovner deformation. Can I erase this?
That's the
But which one?
key. It's a polynomial.
Oh, sorry. Now T has the following property. For the properties. T is free. KT module. And okay, yeah, I have. So here, let me just like this. Grade A to B. See, like this. T exercise on T, T mod just S mod S is my possibility. This is a special fiber because the fiber over 0 and then T minus 1 in fact any non-zero element is 1. So that's why it's called deformation. So now one so how much time will
Yeah, roughly half an hour, maybe less, 28 minutes.
So because of this, that S mod I is the general fiber and S mod initial I is the special fiber, and also that S mod I initial ideal is easier to handle. So one thing of research in commutative algebra is to obtain algebraic properties of S mod I from S mod initial ideal I. This is, I mean, general people does this kind of thing. So for example, it is known that if I an ideal is what is it? Call it it for there is also relations in regularity and Betty number. Okay. So recently, Conte and Barbaro, this is very classical, very old. So, this is the recent result, Conca and Barbaro showed that if I homogeneous ideal A x1 up to xn and this is the monomial order such that from the initial ideal is square free. Square free meaning it's generated by square free monomials, then is what I is one Macaulay. If and only initially it's just one directional. One can find examples where this is this is one Macaulay and Borenstein, but the converter doesn't hold. But in this case, when initial idea is square free, then if and only holds. The same result doesn't hold for Borenstein. So now, in way of similar results, we are interested in the following question. We ask for which so with similarities. We have I say that it's set up and I is ideal. So those F singlet is mod I provided there exists weight ordering W such that F mod initial ideal has those F singlet. So I'm saying that we are asking that whether X mod initial ideal of I has some F singularity, does that imply that X mod I has that F singularities or not? Okay. So we give negative answers for F regularity and F purity. So we give negative answers. The example is consider S to be polynomial in 5 variables. I is a 2 by 2 minus of the ideal matrix. I is ideal generated by ideal generated by 2 by 2 minus of the matrix. Yes, yes. So the So minimum field resolution of this is lesser than the Betti number. If you consider so the proof does that you consider the Grosvenor deformation ring. Okay, you consider the minimal free resolution of this, and then if I go modulo T, because going modulo T gives me the initial idea, and T is a non-zero divisor. If you going modulo T, it gives a minimal free resolution of the X mod initial idea. But if you go modulo T minus 1, then again it will give you a resolution, but 1 is there. So the matrices is not in maximal ideal, so it's not minimal. So you need to remove the free part which are not this, then you get fewer terms. So that's why the Betti number and the regularities are bigger. Sorry, bigger for the initial idea. Yeah. That's how they compare these Betti numbers and minimal free resolution also you can find by the Grosvenor deformation, the large ring and then the then okay. The 2 by 2 matrix is this x4 square plus x5 cube x3 2 1 4 minus. So consider this matrix and the ideal generated by 2 by 2 minus of this, and then this and consider the weight ordering. So first, so consider the weight vector as 6, 6, 4, 6, 3, 1, 6, 24, 6, 3, 1. Then you see that S1 initial idea of this is irregular. But S1I so this ring is not irregular. This was known before. So this is the work of Anurag Singh. So our work is to find a suitable weight order so that its initial ideal is not irregular. Sorry, it's irregular of this. So here characteristic K P greater than 2.
Can you explain what the initial ideal is in this?
In this case, yes. So initial ideal of this again will be ideal generated by 2/2 minus of this. Just you do not write it. That's because the weight is given very less. So it is just x4 square x2 x1 x4 square 4 minus. The same idea. This one is not.
But the minors are not, they're not mononomial.
Yes, but here, I mean, for irregularity, we do not expect that to be monomial because it's a normal, so it's domain. So for the monomial ideal, if we quotient by monomial ideal, they are not domain. That's why we consider that question that is not initial I. I mean, with respect to any weight order, not some
So this
initial.
may not be a mononomial.
No. This, in case for irregularity in monomial ideal won't work unless it's just a variables because it is not a domain, right? If we take it.
As small initial ideal of I in this case. The group which are defined by binomial. Here the 2/2 minus are binomial.
So to prove that it's a variable sufferings of some hypersurface ring. And, yes, and then you can give an particular weight order surface ring of yeah. So this is the example for irregularity, but the example for impurity is easy. Consider the same ring. Okay, now make the characteristic bigger. And then change the order, monomial ordering. Consider the next ordering. With x1 is bigger than x2, xy, and then in so maybe I write the weight ordering less than so in I. In this case, it's a monomial ideal. And for monomial ideal, so x1 in I, f pure by a work of Oxford program. And it's not I, it's also not, I mean, it's not only if regular, it's not impure. It's a I can erase it. Now see the positive answer for irrational singularity. Say the same statement that is k x1 up to xn. I is the ideal of S. Suppose W is the order S. It is more in I. If rational implies that it's for I. And I said that if pure implies if injectivity, but there is another singularity which fits in between. It is strongly if injective. And we also give a positive answer. S I as above. S I W as above. If S mod I, initial ideal is strongly affiliated. Then S mod I is strongly. And then the question remains for if injective singularity.
With any weight order.
Yes, yes. Any weight order is n. I any positive.
It's not a square free monomial ideal is almost never happen.
Yes, because it's domain, right? So that is why we take any weight ordering, not monomial ordering. Because the question doesn't make sense. Yeah.
It will be usually a binomial.
Yeah. Question because it's never going to be domain. But that will be useful in a purity because we just need reduce things. We do not need domain, right? For a purity or objectivity. So for those cases, monomial ordering is important. I mean, we'll see that one consequence of. So now the open question is open question for the injective singularity. I see one useful corollary of a result. So suppose again the same setup is a polynomial ring. I is ideal. Now we consider this is a monomial order. If the initial ideal of I is radical, then S mod I is strongly effective. Particular is if injective. Yeah, I'll just take this too because it's easy. So in I reduced implies that in I is a square free monomial ideal. Then it is famous theory by Hofstadter and Robert that S mod in I, because S mod any square free monomial ideal will be impure. Hence, strongly injective. And then by our results, this result is what I is strongly. And we'll see that this corollary gives a effective way to study if similarities of very combinatorial algebras. So I will just take one.
You have about 4 minutes.
Well, I will just so applications. Polynomial agents. So this is an object in combinatorial commutative algebra. So given a graph, I mean simple graph, one can associate a binomial ideal IG for binomial edge ideal. So I'll not define here, but let's see one example. Like D is just 1, 2, 3. We consider the polynomial ring in 6 variables: x1, x2, x3, y1, y2, y3, and then IG with the corresponding any edge. I'll just associate x1, y2 minus x2, y1, and then with 2, 3, I'll just write x2, y3 minus x3, y2. And then for 1, 3, then x1, y3 minus x3, y1, and give the ordering this. One, y1, y2, y3. We would get this ordering enough. It's just square. Just 1, y2, y1. Then it's more inner is a pure, and by again this thing that so maybe it's radical. What I mean radical because it's a pure, and then by next corollary one can say that it's one IG is a injective. The upshot is that for any binomial edge ideal, to G any graph, and then S mod IG, IG is the binomial edge ideal. Is always a injective. This is pure. But one might ask whether it's a pure or not. It's not. Even for cycle, it is not. And they use this results that binomial edge ideal is always a injective to classify Gorenstein binomial edge ideals. Shows that Gorenstein economic is a path. Yeah, that's the one I said.
Questions?
It also shows that the class of injective similarity is much bigger than aberrational
Yes.
in very concrete terms.
Yes. I mean, not only this, to prove that the algebras with straightening laws are also existing. I need to define what is the algebra with straightening law. Even for Cartwright's complex ideals. So also it is- but I didn't.
That is because there is initial identity there will be mono.
Yes, there will be an ordering such that the initial idea is. That's the point.
Other questions?
Uh, uh, So usually when you do a degen, so you are trying to do some sort of degeneration,
Yes,
and the singularity tend to become worse.
yes.
So what went wrong in that form, for example, why is singularity?
But I should say this is not for any determination, but it's important that it's a problem. I mean, if we consider any affine deformation, one parameter family, then this result is not good. There are examples.
So in one example, you had one example.
Yes, yes,
Regular and then
Yes, yes,
of course. So
yes.
there, the degenerate thing has better singularity than the.
yes, yes. So I'm saying like here that actually the point is that that example, that deformation, if we go modular a non-zero divisor, because that's the thing here. So deformation doesn't hold for a particular. Because
Not really a true deformation.
so the deformation to me, I mean that if you go modular non-zero divisor, it had some property, whether the ring, actual ring has the property or not. Here, with that problem, I mean, if you go into the theory, the problem here is that even for this example, I mean, we pick this example because for this example, for any, if we there is T, here the x5 will be the non-zero divisor. If we go modular that, then it is irregular, but the ring will start with x1. For in general, deformation doesn't hold for irregular. That's
For
the-
us, regularity is different.
Yes, yes, that even for a purity, that is the problem. That is why it is.
Kind of clarity.
The example you have shown that the initial identity of regular with the ring is not. So the key point was to construct example where the initial identity is not a monomial idea.
Now the key point is to find an example where deformation fails. And then with that example, we need to give a weight ordering. You need to give a suitable weight ordering such that the initial ideal is
Yeah, but I mean, wanted to give a better order such a way that the
initial ideal
identity
ideal.
is not a monomial idea.
Yes, I mean, for a regular thing, yes, of
Right,
course.
right.
Otherwise, if it is not monomial, then it cannot be.
Right.
The point is you need to find the suitable order. Because the ring is already there in the vision.
Suitable order that the initial identity
Yes.
is not a
The initial
monomial.
ideal, yes.
Is not a monomial.
And it's not initial ideal.
It is like that.
I think no more questions. Let's thank Mitra for our very next talk.
Okay, so our final speaker in the morning is Mangira Mondal from CMI, and she talked about density function for the second coefficient of the Hilbert-Wurtz function.
Thank you, and I thank the organizers for the. So we are going to talk on density function for the second coefficient of the Hilbert-Wurtz function. So the new results of this talk are partially based on joint work with division. So the outline of this talk is first we are going to give a brief introduction to Hilbert-Wurtz function and then to Hilbert-Wurtz density function. It's not audio. Okay. Am I audible now? Okay. Can you hear me? Okay. So we are going to give a brief introduction to Hilbert-Wurtz function and then to Hilbert-Wurtz density function. And then we are going to study this density function on positive chlorine variety. And finally, we are going to study density function for the second coefficient of Hilbert-Wurtz function on this chlorine variety. So let R be a Noether local link of dimension T and characteristic T. So mostly we will be in this setup. And I is an imprimary ideal and M is a finally graded R module. So either Noether local link or standard graded. So for each natural number, let Q to be T power n, and I bracket Q is the nth Frobenius power of I. So that is the image of the Frobenius ideal, in image of the Frobenius map. So this is generated by elements which are so if I is generated by x some f1 up to fn, so this is generated by f1 power 2 up to fn power 2. So the Hilbert-Wurtz function of M with respect to this ideal is defined to be the length of this module, length of m mod I Frobenius n power n times n. So this is a finite length module. So this function was studied by Kunz when he was studying singularities for Noether local ring in positive characteristics, and he proved this his famous theorem, Kunz's theorem, which Mitra stated in her talk. So during the proof of that theorem, he studied this function, length of R mod I. And later Monsky has shown that this limit here, this limit exists. So therefore the Hilbert-Wurtz length function grows like in the order of Q power T. So there exists a real number HKMI. So thus the Hilbert-Wurtz length function looks like HKMI times Q power T plus smaller order group. So this number is called the Hilbert-Wurtz multiplicity of M with respect to I. So one of the directions to study Hilbert-Wurtz function and Hilbert-Wurtz multiplicity is to study its similarity and differences with the Hilbert-Samuel function and Hilbert-Samuel multiplicity. So A naught R is the Hilbert-Samuel multiplicity. So then we have such an inequality, but D is the dimension of R. Moreover, EHK is also additive, like the Hilbert-Samuel multiplicity. So you take all minimal primes of R, so the dimension of R mod T is the dimension of R. Then EHK MI is sum over EHK of R mod T with respect to I times length of the localized module. And similar to a Hilbert-Samuel multiplicity, this multiplicity also detects the singularity, the regular property of the ring. So if R is regular, then EHK is 1. That we have proved. The converse is true when R is formally unused. So this is another property which is similar to Hilbert-Samuel multiplicity. So Hilbert-Samuel multiplicity detects the ideal up to the integral closure. So there is a operation type closure operation in characteristic T. So let R not be the complement of all minimal primes, union of all minimal primes of R, and take any element C which is in R naught. So that is not in the minimal prime of R, any minimal prime of R. Then the tight closure is given by this definition, and it can be shown that the tight closure is inside the integral closure, and the Hofstad and Huneke show that when J is inside I, both are in primary ideals, then this EHK of R is same as EHK of Ri if the tight closure is same. And the converse is true when R is formally unused. And this is expected because as we have seen in the arithmetic property, Hilbert-Wunsch multiplicity does not detect the embedded prime. So we need to get rid of the embedded prime to get the converse. So another thing to ponder about is that whether the Hilbert-Wunsch length function behaves like a polynomial function, which is not at all true. Unlike the Hilbert-Samuel function, it does not behave like a polynomial function. But under certain conditions, there exists a second coefficient for the growth of the Hilbert-Wunsch function. So first, I am giving an example where you can see that there exists a second coefficient. So let's see is it will plane curve, cubic plane curve. So when C is a cuspidal cubic, this is how the Hilbert-Wunsch length function looks like. When C is a nodal cubic, this is how it looks like. And when C is a elliptic curve, then this is how the Hilbert-Wunsch function looks like. So in all the cases, you can see that there is a constant coefficient for the growth of order Q growth. So the question is whether there exists a coefficient for the Q power D minus 1 order growth. So this was shown by Huneke, McDermott, and Monsky that there indeed such a coefficient exists. So for that we need R to be excellent and normal, and for the purpose of simplicity, I am taking it to be a domain. And so I is a primary ideal limited finally there is a torsion free R module. Then they showed that so the length of M mod I means 2 times M minus rank of M times length of R mod Q. It would compute this length and normalize it by 1 over Q power D minus 1, then this limit exists, and we denote this number by tau Mi. So we are going to recall this number because our result is dependent on this. I mean, we are studying these numbers extensively in our result, and they have shown that this invariant is independent of the module in the sense that they only depend on their divisor plus attached to it. So, let this one and denote the R module by the Frobenius map. Then you can define theta Mi to be another number or another invariant depending on tau. And then they have shown that Hilbert-Wunsch length function has a second order growth, such as the Hilbert-Wunsch length function looks like EHK times Q power D plus beta times Q power D minus 1 plus smaller order. So this is the second coefficient that we will be studying later. So later other people have shown that the second coefficient exists under weaker conditions. And there is a nice result by Bunz and Gubelarev which shows that the Hilbert-Wunsch function for a normal affine monoid ring is a quasi-polynomial and the second coefficient is a constant. So that is quasi-polynomial, I mean the coefficients are, even though they are not constant, they are periodic. So about EHK, it may depend on the characteristic. There are many examples where P actually factors in computing the EHK, and it is also difficult to compute in the sense that even for standard graded rings, in the sense that many usual techniques for Hilbert-Samuel multiplicity does not work here. So for a hypersurface ring, AHK is not the often it is not the degree of the defining polynomial, and also it does not remain same under a flat family. Many times it might take infinitely many values under a flat family. So why do we study a Hilbert-Pool multiplicity then? Because some technique does not work for it. So one thing is that it is a finer invariant. It retains some characteristic key property of the ring, and it is related to other characteristic key invariant in a very significant way, like with F signature and F rationality of rings are often related to Hilbert-Pool multiplicity. Also, for projective curves, we can see that the determining the semi-stability property of certain vector bundles can be related to the value of the Hilbert-Pool multiplicity. So let X be a projective curve over a field, and here is a vector bundle. So we have already seen the definition of semi-stability in the first talk by Dr. Yesterday. But let me recall that if he is semi-stable, then it is a nice bundle. And so this is the definition. For any subbundle, the slope has to be smaller or equal. So this is the Harlan-Alsman filtration for a smooth projective curve. We know that it can be filtered by subbundle. A vector bundle can be filtered by subbundle, such that the quotients are semi-stable vector bundle. And moreover, the slopes of the quotients are decreasing. This the smallest slope here. This is for the minimal slope. So there is a notion of strongly semi-stable bundle when X is over a field of characteristic key. It's called strongly semi-stable if the Fabian fullback of the vector bundle is semi-stable for all iterates of the Fabian. So when K is algebraically closed, Lange has shown that for sufficiently large enough n, the fullback the fullback of the vector bundle has a strong agent filtration. So by strong agent filtration, I mean the quotients here, these quotients are strongly symmetrical. So that is when you pull back the strong agent filtration, you again get a agent filtration. So create a strong agent filtration and then define AI key to be this normalized slope. And Ri need to be rank of the ith quotient. So it shows that I mean K is algebraically closed and R is a normal standard graded V of dimension 2 over K, and X is the curve given by R. And I is a homogeneous ideal of finite pole length, that is length of armored I is finite. Then you can consider this exact sequence here. So this exact sequence here, the last map is given by the generators of I. And he is a Sri bundle. So Trivedi and Bena have independently studied the Hilbert-Pool multiplicity of the projective curves in this geometric term, and this was the first time geometry was introduced to study Hilbert-Pool multiplicity. And they have shown that the AHK of Ri has such a formula. In particular, it is a rational number. So these are, as we have seen in the first talk, these are discrete invariants attached to the vector bundles. So these are studied for the AHK multiplicity.
Here, V is semi-stable in this case?
No, he need not be semi-stable. That's why he has agent filters.
What is AI of V?
AI of V is the normalized slope after you take a strong agent filtration. So there is a strong agent filtration and they do filters. And this is well defined because we are also, normalizing by keyboard. So to study AHK for standard graded rings, the notion of Hilbert-Pool density function was introduced with the Berry. So in this case, we will introduce a grading because we need the grading to define. So grading is needed everywhere. So I is standard graded ring. Need K to be perfect, and I is a graded ideal of finite quotient. And immediate, finally generated, non-negatively graded R. So now for each n, you can define a sequence of functions fn from the positive real axis to the positive real axis. So now here you do not compute the length of this module which we have computed in the Hilbert-Wunsch function. In this case, we compute the length of this module at this floor of q lambda graded piece.
At the
Floor of this graded piece. This is a natural number. So at this graded piece, you compute only the length of that graded piece. So length of m, say this is m. So length of that graded piece. So that is a k module, k vector space. You compute the dimension of that.
sorry, q times lambda is not integer.
Yeah.
It's some real number.
Yeah. So that's why you are taking the floor.
Oh, sorry, the largest integer.
The small, yeah,
Yeah,
largest.
oh, so sorry. Okay, that's what you meant.
For dimension d equals to 1 actually. So finally you want this to be converging to a nice function and you want to study that function to study ASK. So for d equals to 1 it does not converge uniformly. And for d equals to 1 then we also know because it is equal to the E naught. So it's okay to discard it. So take this sequence of functions and it converges uniformly to a nice compactly supported function. Compactly supported and it's a continuous function. So because actually one can show that there is another sequence which is a continuous sequence of continuous functions that also converges uniformly. Therefore, it becomes a continuous function. And EH is related to this function by this integration. So, like the EHK, we want to know what are the properties this density function have. So, it retains some of the properties of EHK. So, such as that it is additive. So, again, you take E to be a set of all minimal primes. So, the dimension is the dimension of the D. And then the Hilbert-Wunsch function of M is the sum of the Hilbert-Wunsch function at each of these R mod T times with respect to I times length of the localized model.
So this previous slide for just once use compactly supported.
So again, it also detects the ideal sub to tight closure. It actually follows from the definition and it's related with the AHK. So and we need R is formally for that only condition. So now the additional property that HK density function has is a multiplicative property. That so here this big A part for each R is another. I mean these are known polynomials, especially in terms of the Hilbert-Samuel multiplicity of the respective B. So therefore it is shown that the Hilbert-Samuel Hilbert-full density function of the Segre product is expressible in terms of the Hilbert-full density function of the factories. So as we have studied the HK multiplicity for curves, let us see what is the density function for projective curves. So again, we are in the previous setup. R is the normal standard weighted domain. X is the curve given by R, and actually it is true for even if R is not normal, but for the sake of simplicity, let's take that. And so P is the CG given as before. So P is this one area. And RIP and AIP are the region data as we have defined earlier. So then the Hilbert-full density function for R with respect to M is given by this description is piecewise polynomial function of degree 1. And the break points are the slope of the agent filtration. So it actually retains those information very nicely. And one can also describe for any I homogeneous ideal of finite colon. I mean, we need the agent data of the middle one also, of this one also. So one can describe that. So we have seen that with HK density function, one invariant that is attached is the Hilbert-Fuchs multiplicity. But then there is another invariant attached to it, which is the maximal support of the density function. So let again, K is a perfect field of positive characteristic, and R is a standard graded thing over K, which is and I is a homogeneous ideal of finite colon, M is a finite standard harmonic and graded. So then alpha mi is the maximal support of the HK density function. So this is proved with division autonomy that if R is a domain, then the maximum support of HK density function indicates the regular property of the ring. So if the support is alpha R is D, then if and only if R is regular. Otherwise, alpha R is less than D. So now there is another characteristic P invariant called F threshold of an ideal with respect to another ideal with some relation between them. So this is the F threshold. I mean, we do not really. So this we just want to say that this is the characteristic P invariant, which was introduced by Mustafa Takagi and Watanabe. So this is shown that the alpha Ri is less than equal to the F threshold of M with respect to I, or I with respect to M. And they also show that in some cases they are equal, and those cases are, I mean, these cases when R is strongly irregular on scalar minus M, or R is a two-dimensional domain and I is generated by homogeneous elements of same degree, then also they are equal. So, so again, we are just giving for the projective curve what happens. So suppose that R is a normal standard graded domain of dimension 2 and I is a homogeneous ideal generated in same degree. Then they have shown that the F threshold is given by 1 minus the minimum slope of the CDD bandit, minimum agent slope of the CDD bandit. But if I is not generated in same degree, then it is different. I mean, the studying of this HK density function is different. And there you have to say that alpha Ri is 1 minus the minimum agent slope of 3T, where 3T is a strong mu reduction bundle of P. So this I can say the definition, but I do not know much about it. So okay.
What is it roughly?
So roughly, so the thing is. So this is here if PIs are not same, then this is not semi-stable. So then you have to take the middle one is not semi-stable.
Yeah.
Then you have to take a agent filtration of that. And so suppose that is some MI given by MI. Then you take VI to be V intersection with MI. And one of those VI will be the mu reduction bundle. And then there is I mean it will be the smallest type where the minimal slope of VI is less than the minimum slope of MI. And then there is a concept of a strong mu reduction. So now we are going to the second part of the talk. How much time I have taken?
Only 25 minutes.
So take K to be algebraically closed field of characteristic P, and so we are going to X is going to be a projective toric variety of dimension D minus 1 over K, and T is a very ample torus invariant Cartier divisor. So with this data, we have a polytope associated to it, lattice polytope actually, and it is a d minus 1 dimensional polynomial. And let Rm denote the homogeneous coordinating of x with respect to the embedding given by D. And CD to be the cone over TD. So I will draw a cone like that. So suppose this is your polytope. So this polytope corresponds to B2 and O3, say. So this is a two-dimensional polytope. You want to embed it in R3. So you are placing it as Z equals to 1 plane here. And you are taking the cone over this polytope. This is your cone. And this is the polytope. This is the Z equals to 1. So we are shifting the polytope if Z equals to 100. So now let PD to be the all points in this cone which are not in the shifted cones, which are u comma 1 plus CD. So suppose these are the lattice points of PD here, and you have to take a shifted cones here. You have to shift this one. So once you take all the shifted cones, whatever is remaining, that is your set. This set was introduced by Ito, and we will call this Ito set sometime. And he has shown that EHK of the Rm is the d-dimensional volume of this Ito set or the closure of the Ito set. So here we are relating the EHK, the invertible multiplicity, with a volume of a topological object, and therefore we can use the combinatorial property attached to this object to study the EHK, which is very typical to toric varieties. So this is what we are also going to do. So this was a earlier result where we have shown that the Hilbert's density function of this of Rm is the d minus 1 dimensional sectional volume of the Ito set. So at Z equals to say at 1 over 3, the HK density function is the volume of this part, I mean this part here. Or at Z equals to 1 plus some epsilon, the HK density function is the volume at this part. I mean this is a two-dimensional thing that we are doing. So in particular, it is a piecewise polynomial function and is independent of the characteristic. So here is an example. This is for T1. So for T1 and with respect to O3, so this is your polytope and these are the lattice points. So at those lattice points, you have taken the shifted cones, and whatever is remaining is in the blue color, that is your Ito set. And the EHK is the volume of this blue color set, and HK density function is the d minus 1 dimensional volume of the sectional hyperbola. So like at Z equals to half, this is your HK density. So for the pair that we have drawn here, using this we can compute the HK density function of this pair. So we know that the HK Rm is given like this Q plus order of Q, and then the HK density function is a piecewise polynomial function, description of degree 2, and the description is given like this. So now the question is, so why do we study the HK density function? Because the existence of this uniform limit gives us a hold onto computing the length function at each directive and then relate it to the EHK, which is somewhat easier than computing the length at once. And existence of this uniform limit helps us to understand many properties related to EHK in terms of HK density. So therefore, one can ask whether there exists such density function for other characteristic T invariants. So such a, I mean, we can ask this for the second coefficient of the Hilbert-Wunsch function that we have introduced in the beginning. So remember that tau was the invariant attached to a finite torsion-free model, such that it depends only on the class of the module in its divisor class group of R. So we asked that whether there exists a density function for this invariant. So what do we want to have a density function? So we want a sequence of functions which converge uniformly to a nice function whose integration will be tau mn. And similarly, does there exist a density function for the beta coefficient? Whether they, I mean, so that is, does there exist a sequence of functions Gn which converge uniformly to a nice function Gr? By nice, we mean maybe continuous, compactly supported. So that the integration is the beta. So this is how we define GNM. So this is actually third. So the definition may look a bit complicated, but it is what we are taking, that we are taking the Hilbert-Wunsch length function at the q lambda graded piece, stored of q lambda graded piece, and then we are subtracting rank of m times the Hilbert-Wunsch density function at this. I mean, this is kind of the innate approximation of q, because we want a rational point here. We do not want any real number. So we are approximating it and multiplying by q power d minus 1. So that when we, if it converges, when we take the limit, it actually goes to, it actually cancel out the first coefficient and measure the growth of the second coefficient. So, I mean, by construction, one can see that this is a completely supported function. So, this is a relatively previously that outside a finite set, this sequence of functions, they converge uniformly to a function GRM, which is given by, we do not want to describe this, but this is given by d minus 2-dimensional relative volume of the section of the boundary of the ecosystem and the form. So with this we get that the second coefficient is the integration of this function, and it can be expressed in terms of d minus 1-dimensional volume of the boundary of the ecosystem. So this example, I mean, we can, with our definition, we can compute GNR, what it is, and with that we can compute GRM, which is the here there is no discontinuity. I mean, even though we have asserted that there can be a finite set where GNR does not converge to GRM, and GRM may be discontinuous at those steps. This step can be described, I mean, definitely, but I mean, in this case, this is continuous, and its integration gives the beta R. So as we have pointed out, the tau coefficient that we want the density function for, it only depends on the divisor class of it. So therefore, if we know it for all height 1 prime ideals, then we know the tau coefficient. So in the toric case, we are kind of in a nice setup because the class group is generated by height 1 prime ideals monomer prime. So let's take gamma to be the semi-group generated by these lattice points here. So gamma is the semi-group generated by this lattice point here. Then there is a bijective correspondence between the monomial prime ideals of R, where R is the coordinate ring of HT, and the faces of the cone CD. And this correspondence is given by, so here, so I'll just draw this again. So this is a facet of PD. This is PD here. So corresponding to that, we have a facet CF of CD, the cone. So we take this facet of PD and we take the corresponding facet of CD, and with that facet, we associate the ideas generated by all the global sections which are coming from the exponential of R corresponds to the facets of the cone, because there is a dimension reversing correspondence between in this correspondence there is a dimension reversing relation that cone. So suppose that R is integrally closed, so we need that for to have the second coefficient. Now then we know that the semi-group actually have all the lattice points and all the lattice point in the cone. In general, that is not true. And take a hydron prime ideal, then corresponding to it, there will be a valuation. This valuation is the unique extension of the support from sigma f. So sigma f here is the equation of this hyperplane which contains CF. The cone can be given by this hyperplane arrangement. So all the facets of the collection of all sigma f will actually define the cone. So the valuation is the unique extension of this sigma f, which gives us a very nice hold how to compute the length related to the hydron prime ideal. Now all the divider monomial ideals of R are given by the submodules whose monomial basis is determined by such a system that sigma f is greater than equal to some integer. Therefore, and then it can be shown that the class group of R is related by the classes of the ideals P. So that F is the subset of this polygon P. So with this hydron monomial prime ideal, we define a small density function. First we define a sequence of functions psi n, which denote the length of this m openness for Q intersection with the prime ideal P, modulo the product of these two ideas, and their Q lambda derivatives. We compute the length of this and normalize it by 1 over P minus. So to study the uniform limit of this function, we have to study the boundary of the echo set. So the echo set is given here. The boundary of this set you have to study, where the boundary is parallel to the hyperplane containing this T. So all the boundary is parallel to this hyperplane. We have to study that. So we are kind of formalizing that. So Hm mu is a hyperplane parallel to the hyperplane given by sigma f, and mu df is all the rational numbers. Here I have to take, actually I cannot take 0, all the positive rational number such that this hyperplane passes through a lattice point of the polygon. Then we define this small density function to be d minus 2-dimensional relative volume of the boundary of the echo set which are parallel to the hyperplane agent given by sigma. So then one can show that outside a finite set, this sequence of functions converges uniformly to the small density function that we have defined. And if we set alpha p to be the small density function minus the Hilbert-Pool density function of this small dimensional ring R mod P with respect to M mod P, then we get the integration of this function is the tau. And because these classes of this function actually generate the class group of R, we can extend this map so there is a group form of vision, and that will give us a complete description of the tau invariant. So with this, we can show that outside a finite set, this sequence of function g and p. So recall that g and we have defined long back. G and m we have defined here. So the sequence of function.
Is there any condition on p on in your definition and p minus 2? If you know word, what is it? P minus 2 is there any special difference or?
We are d is to be greater than equal to 2. We are taking that. For d equals to 1, that is p1, that we can compute separately.
The motivation of defining it.
Because we are using the HK density function. So HK density function, its uniform convergence all is known for d greater than equal to 2. And for d equals to 1, we can know by hand. So we are leaving that. Because for d equals to 1, the d minus 2 dimensional sets are like d minus 2 dimensional faces are the polytope is 1 dimensional. So d minus 1 dimensional faces are the vertices, and then we do not have any number. Okay, so we show that the outside is finite with VDA. This sequence of this finite set also can be described. So this sequence converges uniformly to the function g and t that we have defined earlier. Uniformly to the function g t m. This is a nice compactly supported continuous outside this set finite set, and its integration is the beta coefficient for these hydron prime ideals. So, like the HK density function, the beta density function is also multiplicative, which is not known for the beta coefficient itself. So here A case we have already said that it is known in terms of the Hilbert-Samuel multiplicity of those rings, and GS are given polynomial functions which are known in terms of the second coefficient of the Hilbert-Samuel polynomial. So then there is such a formula. So that is, if you know the beta density function for the second coefficient, then you know it for the second order. And a similar relation one gets if you replace R by a hydron prime ideal. So using that, we get a for the tau coefficient, we also get a kind of multiplicative property. If we know it for two pairs, we know it for their cellular product. For all hydron prime ideals of their hydron monomer prime ideals of their cellular product. So actually, now I have given the stage of the proof, but I am going to first give an example and I will come back to it. So with that, because we have this relation for the product of the toric pairs, here we are going to extend an example by Watanabe. So he has taken this determinant ring. A is a 2x3 matrix with 6 variables, and T is the polynomially quotiented by the the minor 2x2 minor of this matrix. So then it is known that the beta coefficient of this ring is beta T and T is -1/4. Hunnigan, McDermott and Mosky had considered this example because they wanted to show that the tau part is non-zero. Earlier they have given some examples for the tau part is always zero. So now one can see that this is the cellular product of these two toric pairs P1 and P2. And because we have computed for P1 and P2, we can compute for all the hydron monomer prime ideals of R and S, and therefore for all hydron monomer prime ideals of T. So this is the density function for the tau coefficient that we have computed for all II product with S. So this is how we get it, and for all R product with JI, we get this is the density function, and therefore we can compute tau for all these hydron prime ideals. So, and this gives a complete description for the Watanabe example that they had computed for R test product of R and S. So how much time?
More than 10 minutes.
Okay, so then I will just give 3 weeks. So firstly, we actually decompose this etho set into the closure of the etho set into polytopes in d-dimensional convex rational polytope whose dimension whose intersection they do not intersect in the interior. So that is Tj intersection Ti is in the boundary of Tj and Ti. And moreover, the boundary is transversal to the J equals to lambda hydrogen. So then we get the HK density function is the D minus 1 from volume of this set. And to get the we have to study the boundary of this set in terms of the facets of this polytopes Pi. So I will just go to the one-dimensional case here. So here, these are the polytopes. I mean, if we join this here and here, so these will be the polytopes that we are considering. So we have to study the boundary of this set in terms of the facets of this polytope. And the boundary of this shifted form, because the boundary of the set will be contained in the boundary of these polytopes and the shifted. And then using that, we show that GNR is GRM at the nth approximate of the lambda times our constant by Q, and this constant can be bounded by a positive constant independent of lambda. And similarly, we have to study the boundary of the set with a parallel to the hyperplane sigma f equals to 0 to get such a relation for the psi n. And the bound of this correction term here, this actually does not follow only by studying this boundary of the set. For this, we need to use the counting the lattice points of Minkowski sum of rational polynomials. And so if P1 up to Pk are d-dimensional rational polytopes, then the Minkowski sum of their if you count the lattice point of the Minkowski sum of this polytope, then they are quasi-polynomial. And the coefficient of this quasi-polynomial, for that, Henke and Linke has shown that they have certain polynomial behavior. So we extend their result to certain extent to show that these coefficients are bounded. So finally we get that for any d-dimensional polytope, if we take the lambda section of that, and if we count the lattice point of this polytope, these coefficients are bounded. So these coefficients independent of lambda and n, and the top coefficient is the relative volume of this P intersection variable. So this was used to study this correction term, to bound this correction term, because this correction term is a combination of the smaller coefficients of the error polynomial that is there.
Questions? Something I don't know, sensible latest. The first Hilbert forms multiplicity, there was certain vector bundle whose discrete invariance played a role in the determination of first Hilbert forms. For the second Hilbert form multiplicity, you expect the vector bundle in which
So for a complete local domain, it is known that the tau map is 0. So probably that is for complete local domain of dimension 2. So probably that is why they have not done it for curved case. They have not studied. But I have not really checked on it. I can go back and see. But the tau map is 0 because the class group is torsion. So
yes. Okay, and let's thank Andhera for a very interesting talk. So we meet at 2:30.
2 o'clock.
Or 2 o'clock, I'm sorry.
It's an online compared to something.